A little while back, I started working on this Astable Multivibrator. It's one of many different oscillator circuits out there and other classic circuits that you might see around. Well, I really liked the idea of building a PCB on just the primary circuit itself, not incorporating this into anything else or trying to make any kind of elaborate thing out of this, or even, minorly elaborate thing out of it, just the core basic principle. And I wanted to bring that to the channel. So rather than do just a lecture on, hey, here's a feature of KiCad and how you do this, why don't we stop every so often and kind of just come back and just go build a thing? Kind of, coffee with KiCad, if you will, or something like that. That we all maybe work together and you just sort of follow along and we go through the process. Because in the course of going through this, we'll cover everything that we've done in all the other videos over and over again. We're going to have to go to DigiKey. We're probably going to have to make some footprints. Of course, we're going to be routing some stuff. We'll talk about, flood zones and via stitching and, all those other things in the course of learning a very first level basic circuit. So that's what we're doing here today. Now, as I've been reading around on these, trying to do this lab, I've found there's a lot of videos out there, a lot. And they seem to sometimes say different things. And they also all seem to gloss over a couple key critical issues, points, I guess, that were really, really hard for me to let go. I could hear somebody say something. Actually, I take this back because I can't do this. I can't hear somebody tell me something and follow it if I don't understand it. I know there's a lot of people that can go to school, they can see and hear what the teacher says, and they go ahead and they do it and they believe it's the gospel, and that's kind of maybe great because you get through very well. I struggle because if I can't absolutely understand it, it doesn't seem to fit into like a part of your brain that says, I believe this, and if I don't believe it, then I can't apply it. So one of the things that was bugging me was, here's how this goes. They say that when you turn this on, power is going to flow down all of these things, right? You're going to get a voltage down all of this, but what's going to happen is one of these transistors is going to turn on before the other, and just because of impurities or, small little discrepancies in something along the way that causes one to pop faster than the other. So let's say Q1 goes, so the base gets hit here, and now the base has got to be at 0.7 volts to get it to trigger, then the current starts flowing, and then the rest of it goes, okay? So then they would say that, okay, it triggers, and then this starts flowing. What then begins to happen is this capacitor starts charging, and I don't really want to fill you full of like erroneous information. I just want to tell you kind of the problem that I was having. They were saying that the capacitor will start to charge here, that is for the base of this transistor, okay? Then eventually this transistor would charge up to 0.7 volts. It could go all the way up to, like in this case, 9 volts, whatever the VCC is, almost. And anyways, it will get up to 0.7, and that'll cause Q2 to trigger. And when that happens, this will flow, and that will cause this resistor or capacitor to become a negative. Again, I'm being a little erroneous here, but they'd say it'd become a negative, which would cut off the base entirely very quickly to Q1, thereby shutting off the light. So that is kind of what I was hearing. The thing that was the biggest problem, though, was every damn picture I saw has an electrolytic capacitor here, or a polarized capacitor here. And the part I couldn't get to stick was, how does this capacitor charge? So, they just say it. You say it starts charging. It's a capacitor. It starts charging. But where? Where is it charging from? And so then you start thinking, well, maybe it's flowing through here and it's charging up. And, well, if this is charging positive, this is a negative. Maybe all the little negatives are, coming over this way and somehow pushing. No, that's not it, right? And you see this guy right up here, and you think, okay, well, it could be charging from that, but that's the negative side. So what's this doing on this side here, you see? And there's the problem. That is it right there. Also, in practice, if you change this one out to say something higher or something lower, you're going to change the speed at which the lights blink. So I know that this is functioning. I know that this is doing something, but again, the problem is it's on the negative side. So what the hell are they saying charging? And almost every single one of the videos, matter of fact, I think almost every video I watched out there, none of them said this. I had to read, it ended up being one of the actual articles. And it's kind of hard, by the way, to wrap your head around an article without a picture if you haven't gone through this a whole bunch. So anyways, I finally got around to getting into the article, and it does state that I have since figured it out that you can flip the polarity on an electrolytic capacitor. And this was actually, I was in a Quora or Ask, or somebody asked the question, said basically the same thing, what the hell? And what I found out was that electrolytic capacitors, although we're not supposed to charge them in reverse, they can handle up to 1 to 1.5 volts reverse biased. And if this is going to trigger at 0.7, then we end up being fine. And so that's why it works. When I had in my test examples an electrolytic capacitor in there, it functioned and nothing blew up. Okay, so now remember, check this out. So when this starts conducting here, this is going to start pulling down, and then this one here is going to start charging this one positive, this one being less than positive, more negative, if you will. When this one starts to charge up closer, it starts heading up towards 9 volts, but as soon as it gets to 0.7, then that's going to tick on this one right here, which is then it's going to flow through here, start pulling this way, and then the charge is going to start, actually for a time this will be at negative, and that will shut this one off immediately. Right at that point in time, though, this one's going to start charging in reverse again, and then the same thing happens over and over again. Now here is the video, the animation I was talking about, and if you watch it and stare at it for a while, you can begin to see a lot more how this circuit works. Now, I found this after probably, days and days of searching and trying to find information to speak to what I didn't understand, which incidentally, learning how to express your confusion, learning how to express your problem clearly is a thing that you need to figure out. I need to figure out at least. So I found this website, and Paul Falstad does this, and turns out he is the same guy that's been doing these physics applets for I swear 20 years. This website is still the same as it's ever been, almost looks, GeoCities, but it is fabulous. And as far as having some type of an animation to understand, so think about an RF wave, think about multipathing with RF signals. How do you visualize that? Well, he's got a simulator for that. And so this is just a video. You see, it's almost run out. You know what? Here, let me just show you the website. I wanted to show you this because I could make it big. But the applet, yeah, here we go. Let's close this. Here's the applet right here. And okay, if you look at this, I can't make it any bigger, so bear with. But what you can do is you can change, say, the current speed. And then you could slow the simulation way down, bring it way up. The simulation speed was great because when I'm trying to figure out what the charging and discharge and the trigger and non-trigger states are, I really needed to stare at it. But I don't know if you just caught that. When I hovered over this is all entirely interactive. He didn't just make a Java applet to describe an astable multivibrator. He made a circuit simulator. He made a Java, look, there it is without a resistor. How about that? Put it back in. Oops. Now it works again. Isn't that cool? So what you can do is you can start staring at this and you can say, okay, let's see, current's flowing down through this one here. It's flowing. This one here, nothing happening right there. Slowing down. Oh, now it switches. But then you go, oh man, I can't quite get that. Well, let's slow that down a little bit more. Okay, this one's not working, and it's flowing, it's getting there, it's going. And it finally, you look at the little graph. Did you notice there's a little chart up here? So you can, boom, you watch it, and then all of a sudden it breaks and it triggers. But if that's not enough, you can go to this one right here and you say, well, tell you what, can I view that in a scope, please? And I'll get another, well, scope, whatever, I'll get another graph down here at the bottom, and now I can watch it. And if I hover over it, you can see the voltage differential on here, and you could watch as it charges up. And so then this was one of the key points that I wanted to know about, was when does the thing actually go? So now we're up at a voltage differential, of 3.3 volts climbing, and then it's, which one am I looking at? I'm looking at the one on the left. It's conducting, and I really need to be looking at the other one. God dang it. So now we got to wait for this. Okay, so it's off now. It's dropping down to 2.5, 2.4, da-da-da-da-da-da-da. So then what's going to happen? This is the big damn deal I was talking about, that you notice in here it's just a plain regular capacitor. It's going to flip state. So as soon as we're down here into 200 millivolts, and now we just went opposite. Now it just still shows the differential, but we have now reversed polarity. 4, 500, 6, boom. And as soon as it gets up close to, it's at 0.7 volts, I think it's more like 0.69 or whatever, it immediately flips, and then the current starts flowing the other direction. So go look at this. Here is the address up here, falstad.com/everything, But wait, there is more. So here's another neat little oscillator, but this is just what's on the front page. It says, this is an electronic circuit simulator. Yabba-da-da-da-da-da-da. Oh, that's pretty neat. Oh, look, hey, there's a switch. Can I hit it? Oh, by golly, I can hit it. Now watch. This will start cycling through here, get that thing rolling, get the magnetism going on that coil, and then pop, let it loose. And now this shakes and shimmies and wobbles back and forth. Isn't that super cool? So I can say, okay, well, what happens if I increase the resistance? Because right now it's bouncing pretty good, but if I increase the resistance a lot, well, then that's going to attenuate the thing, and that's probably going to cause more problems. So let's get this thing rolling again, charge that thing up, and then break it, and then you watch, boom, 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 and it's going to wiggle wobble back down to 0 really quickly because the resistor is attenuating the thing. Anyways, look at that. So that's pretty cool. But if you go up here, he's got a whole lot of stuff that you can go through. Ohm's law stuff, passive filters down here under transistors. This is where the multivibrators are. You can go through, there's a Darlington pair, more oscillators. So check that out, okay? So this is supposed to be a video on making a thing in KiCad, but I really wanted to show you all this because that really, it made my day. Oh, close, 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 close. To be able to find something like this that you could easily get to, you don't have to have the program on your computer. You can be anywhere and you can study. That's amazing. I hope he has somehow made some money off of this. So then now we'll get back to this. Now we're going to put this circuit together. So of course we have to do our schematic and then possibly make some libraries, but I don't think we're going to have to. But other than that, it's just going to be basic symbols. And then after that, of course, we'll do the writing for the board. I am going to just build this, and you guys are just going to maybe hang around and grab a coffee and sit back and maybe design with me. That's kind of the thought with these kind of videos. If you need a tutorial, if you need more of a tutorial, look back through my playlist, and I've got quite a few different KiCad videos in there explaining all the different processes. Libraries are a big damn thing. So there's a couple in there on that. Okay, so let's go ahead and we'll crank up the schematic editor, and I will put this over on my other screen, and I'll kind of have a mini version maybe up in the window here somewhere, and we'll just get to making this. So as usual, the first thing we're going to do, we're going to go over here to place a symbol, and we'll put this out here, and we say, okay, well, what do I want? I want a resistor. So hit R for resistor. That's the first one that pops up right here. We need 4 of them. So I'm going to place that right there, and I'll kind of zoom in a little bit, scroll in the mouse wheel, hover over the top, hit C, bring it over here, hover it over C, C, and there's our 4 resistors. Don't worry about perfectly placing any of these things yet. Just get the things out and then arrange them. Saves you a little bit of work, I think. So then we want an LED. Do we want an LED? Yeah, we do. why wouldn't we? The thing says that we should. Well, what I was thinking was that maybe we will just put an output there. I think I got an idea. I think I have an idea. Something I was doing on a board recently with solder jumpers. So that if you want to make these little test boards, you want it with the LED and you want it without the LED. Sure, we could probably put a test point in before the LED or something like that just to get a signal out of it. But the LED is probably going to mess with that a little bit if we wanted something more pure, maybe. But anyways, what we can do is we can stick this on the edge. We can make a little solder jumper and bypass the LED. Well, I'll explain as we go. So I'm going to hit, while I'm moving it, I'm going to hit R for rotate, get this thing going in the right direction. I don't know why the LEDs are all the wrong direction in here. I think this is really strange because isn't it, are I not thinking correctly that it's standard issue to have your input or your power source here and your output over there? So seems always backwards. We'll hit C to copy. We'll place another one somewhere over here and we'll go get a capacitor. C for capacitor. There's that one. And yes, we're going to use a non-polarized capacitor because that's what we should use. We'll rotate that. We'll stick that there. C to copy. Bring that over there. So then we'll go and we'll add the transistor. But most of them, like I said, they got a lot more complications going on. It just doesn't pop up like Q right off the get-go. So what you want to do is scroll down here to NPN. But then you need to be mindful of this. You can change this all around and you can get it to work. But what they're showing here is we've got an NPN BCE. So we got base collector emitter is the pins, okay? Of course we can change pins. We can change pins on the footprint. But just remember that based upon the one that you're actually using, the numbers from your symbol library here are going to be matched up with the numbers on your footprint library. So over here is the data sheet for your typical general purpose TO92 transistor. This one happens to be emitter base collector, EBC. You see how that works? So you come over here, BCE, BEC, CBE, it's got every combo, and then nothing. Well, it's alphabetical, so we're in D, so keep going down. Here is our EBC. So now our numbers are correct, and we'll want to remember this when we get to associating our footprint later, and if it's not correct, then of course we're going to have to change it. So then we'll go ahead and stick one of these down here, copy that, put that over there, and that's about it. Oh, what did I want here? I made some stuff myself here. I know what I'm thinking. Forgot. Sometimes I can't find things and I just go ahead and make it. So this is my 2-pin header that I made. I'll hit this. And one thing that I need to do to this is I don't have any polarity on this, so I got to remember every time. So if I'm going to have pin 2 up here at the top, I need to make that positive. So little things like this in your libraries, they work, you get by with them, and then as time goes by, you're like, oh, that's a bummer, I'll have to remember to do that. You want to get around to doing that sometime probably. So I'm going to put this here, and now I'll start wiring things together. If I look back here at this schematic, should I put these up and down and over like that, or should I just put them in a row? It's up to you. I can't really see any big reason why you need to do one or the other there. So get rid of that. I'm hitting escape, and then I'm going to hit M for move. I'm just going to put these all right in a row, but I will kind of keep them sorted together. I'm not going to go so far as to measure the dots between each one of those. That's getting a little bit crazy, I think. And then we're going to wire these up. So we'll go from here, and I do like this idea, come around like this and go here. Don't just wire straight across the top, okay? We get there, there, do. Make sure that when you do make a junction that it actually gets the junction on there, because I have had instances where it doesn't show up and it's actually not connected. You'll find that out in your electrical rules check later, right? Then this LED, I'm going to move it down a little bit because somewhere around here, let's see, I got to do that bypass thing I was talking about. Let's get these in line first. See, I shouldn't have even really started running the wires yet because I might squish myself up here. Oh, and this is kind of a bummer because you want this thing to be nice and symmetrical. I can flip-flop these things around a little bit here, you know, if you really want to. There we go. Okay. So this looks like it's working right. And I guess I would, if that was going to be the case, I'm going to put this one over here, put this one over here. If it helps you understand the circuit better, then I think that's probably the most important thing there. And don't break any company design rules, you know. If you sit down with you, your team, or you, yourself, and I, and you decide that this is the way you want to do things, continue to do it that way, I think. So everything look okay. I should get this in line with that. Hit W for wire. I don't usually do that though, because if you hit W for wire, it just starts from wherever you are. Sometimes it's kind of hard to know that you're right over the top of the thing. But if you do hit W once, it's still on. So then you can just click away. Oops. Let's get that in line. I think it sounds kind of like I'm getting the sniffles. Sorry about that. Okay. Now here's what we got to do here. So this one, because we don't get to make a cute little diagonal line. We'll go over here. Yeah, see, that's going to be a problem, ain't it? I don't like this. Don't like my placement. God damn it. Okay. Frick. All right. So there's that. And then we'll ground down here. Negative. All right. So that's the circuit. I think I could have made it look a little bit nicer, but you know, it's going to do the job for us. Now, the next thing, of course, we need to do is annotate everything. But before I do that, I want to add some test points in here, and I want to maybe add this little LED bypass. So, you know, kind of what I want to have here is another 2-pin header, which is probably going to cause me to screw this thing all up because it's going to be too big to put in there. And then what will happen is there'll just be kind of a jumper of sorts that you just you know, maybe you've used these before, maybe you've seen them somewhere or another, but instead of using like a 2-pin header that you have the little plastic thing that you stick on top, right, that you could lose, you just make some pads on the board that are very close together, and you can just solder a blob across, and it's a real quick, fast way to make a little switch for yourself. So I'm going to add some of that stuff in there, and like I said, test points. So the test points, where do you want these to go? Don't think terribly super logically. Let's see. Don't really think like a real smart, you know, EE on where you're going to stick all your test points. Think, where do you want to know something? If you were to put a test point right here, here, and here, somebody's going to say, why'd you put all 3 right there? Everybody knows that those are all going to be at VCC. Why the hell did you do that? Well, maybe you didn't know that. Maybe you never got that proven to you, and you want to make sure that it's a fact. Maybe you just did Kirchhoff's voltage law, and you want to put a test point right down here, and you want to check to see if that's at 0 volts to ground. You know, even though it's horribly obvious to most people that it probably is. Throw one in there anyways, okay? And possibly even if you did want to have more than one ground, you know, you could stick one here and one here and one here, even though on the board you're going to put one way over here and one over here because you think that might give you, it'll be easier to get your probes to. So I'm going to go rejazz this around a little bit, and then I will be right back. Well, I'm here. I've got it done. I've got my thoughts laid out on here pretty well. I've got my test points where I want them. I've got these little bypasses where I want them. But as you can see, it's pretty messy, and so I want to clean that up. Now, to go over first, though, the test points, I wanted to show that I put, of course, you put your positive, negative here, so we can check voltage there, or I can have a ground point to clip onto and then be able to probe wherever I want. I have a test point here that is just prior to this mess, which will be for either an output or just checking voltage, before the LED, I guess. Same over here. And then down here, I've got test points on either side of the capacitors. So if I wanted to, I could either, from ground to here, I could check the voltage here and there, or I could check the differential or the charge across the capacitor right there. So that's good. I'm going to spend a little bit more time cleaning this up. So, when you're making things, I guess, like I said in the beginning, you drop it all out here, you kind of arrange, and then you run out of room, and then you kind of got to redo it. So what I feel like I'm going to do is try to save it the best I can without having to redo the whole thing. So in the fast motion, maybe you caught me doing this. I just sort of grab some of this and start pulling pieces apart. And I feel like if I can keep them lined up, as in vertically, as long as I don't do this too much, then I should be able to pull this out and give myself some more space. Now, I'm not going to try to make this super perfect because this is not for production, and I am trying to, walk the walk and such as far as like keeping things good and clean, but this is just a for the fun of it circuit, so I don't need to be too complete protocol, but I don't want to break the rules. So we'll move this over here, and then this I can go ahead and just get rid of. So I want my test points out far enough to where I can read them. Move that up there. Now see this test point, actually I could hide that. You know what? That'll actually clean up a lot right there because I wasn't even thinking about that. I don't need to see this. If I see TP whatever, I know that's a test point. The symbol here, I know that that's that, right? So I could go ahead and just make that invisible. Watch out on, I don't know what version I'm running right now and where I'm at, but I've noticed that in different windows now, they don't have invisible, which is weird. You're looking for invisible and you don't see it, and you're like, what the hell, where'd it go? They've got a check mark for visible, and so then you have to uncheck it. And then this one right here will do the same. Move that up around here. See, that's going to help a lot, but we'll still move that test point over a little bit, and then I guess we could just connect that. So I think I'm going to call that good right now. Now, you see what, from the start to what we've got now, this is a lot better. Everything is pulled out a lot more. It's easier to read. Hid all of the extra values that I didn't need to have. I guess I could get rid of, no, I'll leave those there. But I hid all that stuff, moved the values, again, that I did want out into a place that seemed reasonable. Now, I did have a handful of problems, and, depending upon how I edit this thing, you'll see that in the course of moving this and spreading it all out and deleting lines and everything, and I started connecting things, and it's getting late, and I'm getting kind of dingbatty, was connecting things in wrong order. So, make sure that you refer back to your original schematic or original plan and keep that going good. So then after that, then you do your annotation. Now the annotation, it does it, it's got the, the auto annotate, and it did it mostly fine. It put 1 and 2 over here, and 1 to R1, R2, R3, and R4 right there, and that was good. But the test points, I wanted them a little bit differently, and here's more of the point to this, is you can run the auto annotation, and maybe you probably should, but a lot of times things kind of go together. For example, these test points down here around the capacitors, my thought primarily is to check the charge across the cap, and so I probably want them sequential, and the same over here. Now these up here, these are going to be for the outputs, right, from the main oscillator output, so I want those common. So I had to come through and rename them manually because it didn't do that properly. But that's no big deal. Just hover over, hit E for edit, and you hit 7 because you already see that it was highlighting the number, and you hit OK. So again, E6, enter. Right? What else? What else? What else? Just mainly give yourself lots of room, make things very clear and easy to see. If you feel that this title block, right, or I mean the whole entire border here in the title block is getting in your way, because I mean this is just a little multivibrator circuit and it's already taken up the whole space, golly gosh, what are you going to do? Well, you can come up here and you can go to your page settings and you can change it. So, I mean, if you need to, because we're not going to use it for anything anyways, change it to A0 or something, right? Make the thing huge, you see? Look at that. Ooh, we've got lots of room now. And then I can grab the whole deal. Oh yeah, now we're talking. So, you see? That, for some reason, sometimes people, they don't know that you can do that, and you feel like you're getting very constrained, and you got to be really, tight on space. So the next thing then, after annotation, electro rolls check, and then we got to do the association, and then run our netlist, and then we'll move on over to the PCB editor. We probably will go there and probably come back here because there's probably some more things that get kind of messed up along the way.